Hello, my name is Sanyasi Bobbara. I come from Kingston University and I work with Professor Jean-Michel Lindsay. So we work on, I'm from physics department basically, so my job is to characterize the solar cell. I don't prepare solar cells, my chemistry colleagues, they make solar cells for me. So I work on this experimental technique right now. I'm building upon the technique called CELIV. CELIV, charge extraction by linearly increasing the voltage. So this is a technique you use to measure the mobility and the recombination rates of charges simultaneously, which is not possible with all the other techniques like doing it simultaneously. So that's a good part of it. And I'll explain what's the sample we use. So we prepare basically an organic photovoltaic cell, a bulk heterojunction cell made up of the active medium is P3HT and PCBM, and it's an inverted type bulk heterojunction solar cell, which is more stable than the regular traditional solar cells, regular ones. And coming to the technique here, so this is set up for CELIV, and so in CELIV there are again two parts, dark CELIV and photo CELIV. So the experimental results you see here that I'm going to discuss shortly are dark CELIV. But the setup here shows both dark and photo CELIV here. So I will quickly go through the setup here. Okay, so this is a sample here. This is placed on an optical microscope. So we scan very small area like micron, like or 2 micron by 2 microns area, and focus a laser pulse on the sample. And at the same time, we use the sink to trigger an arbitrary waveform of ramp kind of signal. So what we do is, in this setup, you excite the sample like photo-generated charge carriers, create the carriers, and you maintain the sample at an like open circuit voltage, so that it's kind of a flat band conditions where the photo-generated charge carriers, they float in the sample before being extracted. So when it excited with an optical pulse, you create photo-generated charge carriers, make them float in the sample, and followed by a ramp signal in a reverse bias conditions. So that kind of extracts those created charges, right? So with a dark CELIV that is without the photo excitation, you get as I said, like the dark CELIV, you get to study what is the mobility of the charge carriers generated already in the sample. With the photo CELIV, you can create charges, and if you can like study the time delay between the photo excitation and the electrical excitation extraction, you can see how the charges are recombining after some time. So that's basically the setup there. So that's basically the setup. Here is the experimental result that I got. So one of the cells that I've tested, and I use different ramps. Like I change the ramp rates, so I can extract faster and faster and faster by increasing the ramps. So that's what is here. So with a low ramp rate, you are extracting the charges slowly, and you see a bump somewhere later. With a very high ramp rate, as you increase the electric field across the sample, you're extracting the charges quickly. So you see the shift in the peaks. So with this known information, as I described here in this picture here, I can figure out what is the mobility of the charges for different electric fields you're applying. So I plot the mobility of the charges as I change the electric field or the voltage applied across the sample. You see a positive slope. So which means you're extracting. What you're doing is you're applying an electric field across the sample, and when you do that, you're trying to tilt the Coulomb potential across the sample. Like for each molecule, let us take for a single molecule, you're tilting the band, the Coulomb potential band. Okay, So that way you're extracting more deeper and deeper charges. So which means you get more and more mobility for higher electric fields. However, for the similar kind of sample and at the similar temperatures, there has been some published result which shows a negative slope, which means like as you increase the electric field, there is a decrease in mobility. So right now, I'm still trying to understand what's going on with the samples, but what I think is it has to do with competition between an energetic disorder and positional disorder. Depending upon which one dominates the other, it can be positive or negative slope. So right now, I cannot compare exactly to what the published results are, which is like having a negative slope. So, but we are still working on that to understand what's this behavior here for. So, yeah. So we are more concentrated right now. I'm focused upon developing this technique, and then we'll go ahead with the changing the samples, and there are different kinds of samples which are of much interest we would like to probe. So that's pretty much it.
Now between the valence and conduction bands, you've got a forbidden gap. And if the gap you've got is just too wide, you'll lose your photons in a snap. Now if the gap you've got is far too narrow, you'll catch the whole darn fleet. But that won't do you any good, 'cause all you'll get is heat. Oh, solar energy, yes, solar energy. We can have our fun with the power from the sun using good old